So in a similar vein, it might also be useful to look at another monitor command. If we do monitor interface traffic, now we can see here for every interface on the system, we have a live updating record of the packets per second going in and out. Now on my box right now, it's not too interesting. There isn't a huge amount happening at this moment. If I press B, we can see that shifts from packets per second to bits per second. We're only occasionally seeing the GE000 interface jump up from 0 bits per second in output and input. And that's because we've got OSPF hellos going in and out there on that interface. So just enough to give us some statistics, but no live traffic in my lab at the moment. But you get the idea. This monitor interface traffic gives us a nice way to quickly review, the levels of traffic on the device. Like I said, hitting B shifts the view to bits per second. Hitting P on our keyboard shifts it back to packets per second. And we've got some help at the bottom there to remind us that we can use Control U, Control D to page up and down when we have a device with many more interfaces. Let's hit Q to escape that. We just mentioned that we had OSPF running on this box. So if we maybe show OSPF neighbor, I can see here on GE000 I have an OSPF neighbor that I'm in the full state with. Let's do monitor traffic interface. Now be careful here. We just looked at a command a moment ago, monitor interface traffic. Now it's not very helpful on Junos' part, but monitor traffic interface is something very different. This is basically TCP dump. This is the ability to dump as text decodes of packets on the crossing that interface. Actually, I should be careful, not crossing the interface so much as coming in and out of the RE on that interface. So let's do monitor traffic interface G000.0. I don't want any DNS resolution. That could slow things down. Plus, I don't have a DNS server configured in my lab. And maybe I also want to make sure that I capture, the full packet size. And so that's 1518 on my Ethernet interface. All right, so we can now see decodes of the packets coming in and out of the system. And we see that the OSPF version 2 hello packets, they're coming from my interface's IP address to the reserved multicast address for an OSPF hello 224.0.0.5, and they're going to keep going back and forward, in and out, in and out. I can even rerun that command and make it detail. If I make it detail, I'm going to get an even more verbose decode of the packet. Stop that. So there we have just 2 packets decoded at this date and timestamp. 1 packet came in, IP header, various details in the IP header, including source, destination. On top of that, an OSPF header that's a hello, and then a decode of the OSPF hello contents. What router ID, what area 0, what area, in this case area 0, dead timer, hello timer, on and on. So we have looked previously at trace options inside of Junos, and that's a very powerful way to troubleshoot, but now we see another way to troubleshoot. Without any configuration at all, this monitor traffic interface command allows me to dump and decode live on the CLI packets that are coming in and out of the routing engine. And that's very important. It's not going to try and decode transit traffic. Stuff coming in on a 10 or 100 gig interface and going out on another 10 or 100 gig interface somewhere is most definitely never going to be seen here. And that's a good thing. This is the routing engine we're running this on. We don't want to kill the RE CPU and memory by trying to decode 10 or 100 gigs per second. But it's very useful to be able to decode the packets in and out from the RE, with respect to routing protocols, spanning tree, SSH, telnet sessions, ICMP pings, or ARP on an interface. All of this stuff can be seen here with monitor traffic. Maybe one last quick note. If we get rid of that detail, we can actually add a hidden command. Because it's hidden, we can't autocomplete it. We have to type it out in full. But if we write file, we can now specify mycap.pcap, .pcap being a file extension used by the popular popular program Wireshark. So if you haven't used that, I'm sure you have, but if you haven't, it's a GUI, allows us to load these PCAP files and look at the decodes of them, do some nice advanced searching and filtering, and maybe a little bit easier to look at the first time if you're not used to reading the raw ASCII, the raw text decodes above here. And we let that run, give it a few seconds to accumulate some OSPF hellos. And eventually, when I'm happy, we can Control C. We talked for just long enough for it to capture 2 packets. It tells us after hitting Control C and closing it. And if we file list, we can see, yep, PCAP, mycap.pcap is now there. And we can copy that off the box with FTP, FCP, and load it up in our Wireshark or similar favorite program for looking at packet decodes. So here we're simulating a console connection to the serial port of a device, and we're imagining that for whatever reason we've basically lost the password. So it doesn't matter if this is a virtual MX or a virtual SRX or a physical device, the process is the same. What we're aiming to do is interrupt the boot process. So right now we're at a screen where I've seen the kernel begin to boot, and I've had a chance to basically hit the space bar to get the prompt that you see in front of us. If I'd hit enter or just waited a few more seconds, it would have carried on booting as normal. So if we type boot and hit enter at this point, we would simply let the system continue booting as normal. But what we're going to do instead, in fact, is boot space -S. And when I hit enter now, that's going to tell the system to carry on booting to carry on booting in single user mode, basically disabling the requirement for a password to reach the Unix shell. So let's let that carry on. It'll take a little while to boot up. So we'll see all the normal D messages, boot messages scroll by, various hardware on the routing engine being initialized, our FXP0 management interface, file system checked for it being clean and mounted. And then eventually it's going to come to a stop, and right now we can see on screen it's asking us, enter the full path name of a shell or recovery for root password recovery. So obviously we are going to type recovery to get to this CLI and be able to actually change the root user's password. But the other alternative here would be to accept the default and have it start a Unix shell, so bin shell. By typing recovery, we have a script executed in the background that just gets the system into a clean enough of a state, booted just enough in single user mode for us to access the CLI and actually change that root user password. So let's type recovery. It'll carry on booting and mounting its file systems. Right, and you can see, it's finished booting, and now we've been dumped into the CLI and we haven't been asked for a username or a password, and the CLI prompt tells us, we are the root user at our JR2 host. And in fact, above that, we've also seen that, not standard, we've got a section of notes reminding us how we actually change the root user's password. I hope we know that stuff off the top of our head. We've been playing with Juniper for a while, but it tells us go into config mode, set system, and then our root authentication. And we're going to say plain text password. It will be stored as a hash password, but this keyword is just allowing us to enter our password in plain text and confirm it. Right, and then commit. And we can exit. So we exited the configuration mode after committing. We exited the CLI one more time. And then it asks us, would we like to reboot the system, which we definitely do because we're currently booted in single user mode. We want to get back the system in a normal state of operation, but critically now we know the root user's password. Happy days.